Hello students and welcome to this next lecture in our revision series of physics for class 11th. So today we will continue with the section of work by energy and circular motion that we were discussing in the last couple of lectures. So let's take it from here. So in the last lecture we had discussed about conservative and non-conservative forces and the application of work energy theorem and the relationship between potential energy and internal conservative force. So we had seen that potential energy and the internal conservative force or forces in a system, they are related by this equation that delta U or change in potential energy is negative of work done by the internal conservative force or minus of F internal conservative dot ds. So we will look at this relationship a little bit more closely today, the relationship of potential energy and internal conservative force, and understand a few more aspects of this before we come back to more applications of work energy theorem. So this relation can also be interpreted in such a way that for a small displacement ds or for a differential displacement ds, the differential change in potential energy is minus of F internal conservative dot ds. So this is the way of understanding it at a differential change level. Okay. So suppose we have for a one-dimensional system this particular equation. So we have a one-dimensional system. Okay. Let's say that is along the x-axis. So what happens here is that the internal conservative force has just one component, and that is along the x-axis. And the displacement in general also has only one component, that is along the x-axis. So this relationship above reduces to a simple product like this. So we can see the relationship between the internal conservative force and potential energy is this. So this equation above tells us that if we are dealing with a one-dimensional system, along the x-axis, the potential energy will be a function of x. It will be a scalar function of x such that the internal conservative force this will be negative gradient of potential energy. So this relation is written like this, that it is the negative gradient, one-dimensional gradient, that is d by dx of the potential energy function. So this is what we take away from this above relation. So this equation below is like the inverse of the above equation, that du is equal to minus f dot ds. Okay. So let us look at a couple of examples of this. So some okay with a particle of, let's say, mass 2 kilograms under the action of only a conservative force F, such that its potential energy U is, let us say, equal to a relationship like this, where A and B are positive constants. X is position or X coordinate in meters, and U is the potential energy in joules. Okay. So first of all, given that A is equal to 10 joules per meter to the power 4 and B is equal to 20 joules per meter to the power 4, sorry, meter square, find F, that is the conservative force at X equal to X. And secondly, from that, we will find the equilibrium points for the particle. Okay. And we will understand whether these equilibrium points are stable or unstable. So we will show which of them are the stable equilibrium points and which of them are the unstable equilibrium points. Okay. And finally, we will see that if the particle has a kinetic energy of, let us say, 60 joules at X equal to 0, the maximum kinetic energy, and B, the maximum displacement from X equal to 0. Okay, so let us try to work out this question on the basis of what we have learned about the relationship between potential energy and internal conservative force in a one-dimensional situation above. So just try out this for a minute. We will discuss this question. Okay, so let's understand this question in detail. So what is happening here is that by substituting the values of A and B that are given to us, we can see that the potential energy function is equal to here this much. Okay, so the internal conservative force will be given by this derivative. So it is minus of the gradient of this function. So as you can see, it will become minus 40x cube plus 40x. This is the formula for the force as a function of x. This is the force at x equal to x. So for example, you can see that now when I want to find the equilibrium points, second part, we can see those are the points where the force should be 0. So I'm having 3 equilibrium points. X equal to 0, x equal to plus 1, and x equal to minus 1 in meters. There are 3 distinct equilibrium points. Okay. Now about stable and unstable equilibrium points, as you know, the stable equilibrium point are local minima of the potential energy function, and the unstable equilibrium points they will be local maximas of the potential energy function. So here, as you can see, the potential energy function was given to us by this relation. So if we have to look at the graphical representation of potential energy function, we would see that we have this kind of a shape. It has a local maxima at x equal to 0 and 2 symmetric positions at x equal to plus 1 and x equal to minus 1, where the potential energy function has a local minima of minus 10 joules. Now from this we can understand also that why the x equal to 0 is a stable equilibrium point, not unstable, because not only because it's a local maxima, but also because if you see at x equal to 0, this is 0, so force is equal to 0, but at x equal to plus of delta x, okay, the force which was, remember the force was given by this relation, this will tend to be a negative quantity. Okay, for example, if you take delta x as this much, you can see that this quantity 1 minus delta x square will be negative. So the force will tend to be positive, which is greater than 0. Whereas at x equal to minus of delta x, this will tend to be negative. You can see that the force will become negative. So that means the force is non-restorative. At the point x equal to 0, the force is 0. But the moment we go to a point plus delta x, the force is positive. Or if we go to a point minus delta x, the force becomes negative. So it is non-restorative force. Okay, with respect to x equal to 0. So therefore, what happens? X equal to 0 becomes an unstable equilibrium. Okay. Whereas on the other hand, if you look at these 2 points, x equal to plus 1 and x equal to minus 1, okay, you can see the force is 0, but at x equal to 1 plus delta x, for example, x equal to 1.01, you can see that the force will become negative. At x equal to 1 plus delta x, the force is becoming negative. And at x equal to 1 minus delta x, for example, x equal to 0.99, the force will become positive. So at x equal to 1 minus delta x, the force is becoming positive. So from this, we can understand that with respect to the point at x equal to 1, the force on either side of it is restorative in nature. If I go to a point 1 plus delta x, the force here is negative. If I go to a point 1 minus delta x, the force here is positive. Okay. So we have restorative force with respect to x equal to 1, which is an equilibrium point. So hence x equal to 1 becomes a stable equilibrium point. And we can similarly make an argument for the point x equal to minus 1 meters, which will also be a stable equilibrium point. Hence, our equilibrium points are distributed in this way, that x equal to 0 is our only unstable equilibrium position. Whereas x equal to plus 1 meter and x equal to minus 1 meter, these both are these both are our stable equilibrium positions. Which you can again verify from the graph of the potential energy function given to us versus x. Plot this potential energy function as we've just seen earlier, we will get it's kind of a graph. So these two will be our symmetrical stable equilibrium positions where the potential energy has a minima of minus 10 joules, whereas the origin will be our unstable equilibrium position where the potential energy has a local maxima of 0 joules. Okay. So we'll just review this solution once up to this point, and then we'll come to the last part of it. Okay, so now let's come to the final part of the question, where we've seen that if we are giving the particle a kinetic energy of 60 joules at the origin, what is the maximum displacement it can make? Okay. Want to find the maximum displacement it can make, and we want to find the maximum speed that the particle can have. Remember, the mass of the particle was given to us as 2 kilograms. Okay. Now see, what is happening is that because only internal conservative force acts on this particle, external force and non-conservative forces are absent. Okay. So mechanical energy is conserved. We will use that aspect. So change in kinetic energy plus change in potential energy is zero. Or you can say that the sum of kinetic energy plus potential energy is constant. Okay. So now we can see from the given information that we have, at x equal to 0, the kinetic energy is 60 joules and the potential energy is 0, because remember the potential energy function was this. Okay. So therefore the total mechanical energy is 60 joules. So from this we can understand also that now we can see that the minimum potential energy that the particle has at any point of time is equal to minus 10 joules at x equal to +1 or x equal to -1. You can see from the graph above, we have figured that out. So therefore, maximum kinetic energy will be equal to the total mechanical energy minus the minimum potential energy. So the maximum kinetic energy the particle will have will be 70 joules when it is either at x equal to 1 meter or x equal to -1 meter. Okay, so from that we can see that the maximum speed the particle will have is square root of 70 meters per second, because the mass was 2 kilograms. Okay. So that's one aspect of it. And also now we want to see the maximum displacement. So when the particle reaches maximum displacement, its speed should become 0. So kinetic energy should become 0. So the potential energy should become equal to the total mechanical energy. So 10x to the power 4 minus 20x square should become equal to 60 joules. So we can see we have this sort of relation. Okay. Now obviously see, we can see that x square cannot become negative. So the only root we will take is that x square is 1 plus root 7, okay, which is approximately will become plus minus of square root of this. Okay. So this is the position at which B becomes 0. Okay. So in other words, if you go back to that graph of, first of all, potential energy versus X, that graph is like this. Now it was, if we talk about the total mechanical energy in that particular problem, it was 60 joules. Okay. And the potential energy's minima was minus 10 joules. So you can see that these are the 2 points at which the kinetic energy will become 0. At which the potential energy becomes this much. Okay. Because the kinetic energy becomes 0. Whereas at the origin, the kinetic energy was 60 joules. At this point, plus 1, and at this point, minus 1, the kinetic energy was 70 joules, which was maximum. Okay. So this is the complete conclusion of this particular question. Okay. Now from this we will move on to 2 and 3 dimensional situation of potential energy. So let's go to the general case. For a 3-dimensional system in the XYZ coordinate frame, okay, potential energy will become a function of X, Y, and Z. It will be a 3-variable function, and the internal conservative force will be having the 3 components Fx, Fy, and Fz. Okay. So for the relation, okay, which is coming from basically from this, the differential displacement will also have in general 3 components. Okay. So this relation above further reduces to the dot product with a minus sign. So this particular relation. So now the inverse of this relation becomes that the X component of internal conservative force is negative of partial gradient of U with respect to X. The Y component of this is negative of partial gradient with respect to Y. And the Z component is negative of partial gradient with respect to Z, where we understand that is the condition for this under the special condition that Y is constant and Z is constant, or delta Y is 0, delta Z is, that is the meaning of the term partial gradient. Of U with respect to X. This is the meaning of the term partial gradient. So this becomes an important set of relations for here. And we can also use the gradient operator to define this. So we can use the vector gradient operator, or what we commonly call the del operator, which is a vector operator which, applying on a scalar quantity, gives its three-dimensional gradient. So using this, we can see that the internal conservative force is negative of the gradient operator of potential energy. So as a simple example, if we have potential energy is this sort of function where x, y, z are coordinates in meters and u is potential energy in joules, then the internal conservative force will become negative gradient of potential energy, which means that it will become minus of this. Then the y component will become negative of partial gradient with y, and the z component will become negative of partial gradient with respect to z k cap. Okay. So now calculating the negative partial gradient with respect to x, we have to keep y and z as constants and differentiate with respect to x with a minus sign. So this will become minus 6xy, okay, minus z I cap. Then doing the same thing with respect to y, so it will become minus 3x square j cap. And then doing the same thing with respect to z, this will become minus x k cap. So this will become the expression for our internal conservative force. It will have three components such that the x component of the internal conservative force will be minus of 6xy plus z. The y component of the internal conservative force will be minus 3x square, and the z component will be minus x. So this is the example of the application of this concept, that internal conservative force is negative gradient of potential energy. So make sure you go through this section carefully once before we discuss more examples. All right, so let's look at another example of this. So this time let's consider a two-dimensional situation. A particle moves in a two-dimensional plane, the xy plane, such that its potential energy is given by the relation alpha upon square root of x square plus y square, where x, y are in meters and alpha is, let us say, 20 joule meters. Now, assuming only internal conservative force acts on it, and its mass is m equal to 5 kg, find the particle's acceleration at 3,4 meters. And secondly, if the particle is projected with v equal to 2 I cap in meters per second from the position 1, 0, find the maximum displacement it will make. Okay, so just give this question a try. We will discuss this in a moment. Okay, students, so let's understand this particular question. So potential energy is given to us by this relation. Okay, so from this we can see that the internal conservative force be negative of gradient of potential energy. So that means over here that the x component of the force is negative of partial gradient with respect to x of this function, which means that we have to treat y like a constant and differentiate it with respect to x. So that will become okay. So as you can see, this will become and similarly the y component of the force will become negative of partial gradient with respect to y. So repeat application. We get this particular expression for the y component of force. So putting together this vector relation now, the internal conservative force is given by this relation. Okay. Which you can also simplify and see like this, that if we treat the position vector with respect to the origin, the magnitude of the position vector as this, then this force can also be shown as, or it is the typical central force, inverse square law type of central force given by this relation. Okay. But for us right now, this is sufficient. So this is about the force. So the value of alpha is given to us as 20 in SI unit. Okay. And the mass of the particle kg. So at the point 3, 4, the force will become alpha upon okay. So you will see that alpha's value is 20. So this will become 20 by 25 into 0.6 I cap plus 0.8 J cap, and we calculate it. So the force will become so you can see that the magnitude of the force will become 0.8 newtons, and the direction will be along the unit vector 0.6 I cap plus 0.8 J cap. So that being said, now we can calculate the acceleration of the particle by just dividing by the mass. So further, since the mass of the particle is given to us as 5 kilograms, the acceleration is going to be this force divided by mass. In meters per second square as a vector, its magnitude is 0.16 meters per second square. So this is about the acceleration when at the position 3, 4. Next, let's look at the second part of the question. So from this position 1, 0, we are projecting it along the x-axis with a velocity like this. So we have to find the maximum displacement it makes. Sorry, the projection velocity should negative x-axis. We'll just make a correction here. Okay, so let us understand this situation now. So what is happening is, in our two-dimensional xy plane of motion, we have taken a particle to this position x equal to 1 meter, y equal to 0, and given it a projection velocity along the x-axis. Or rather along the negative x-axis of 2 meters per second. Okay. So this particle P, now we know that the potential energy was given by this relation, where alpha was 20 joule meters. So from that we had got the force as 0.8. No, in general we had got the force as an expression like this. Okay. So you can see that at 1, 0, the force acting on the particle will be along the positive x-axis. Be like this. Okay. So because of that, the particle will tend to decelerate. So this will be 20 I cap in newtons, the force, because alpha was 20. So because of that, the particle will tend to decelerate. So if it started from here at t equal to 0, by the time it reaches somewhere here, its velocity will tend to get less, but the force will tend to remain like this. So when it reaches some general coordinate, the force at that general coordinate will be of this type. So the particle has a variable acceleration, or you can say it has a variable deceleration as it moves from that position 1, 0 towards the origin. So if it finally comes somewhere here and stops, if it comes to some coordinate and stops, okay. So between the initial position and this final coordinate, if we apply work energy theorem, So let's say this initial position is our A, and this position where it stops is B. So from A to B, if we apply work energy theorem or conservation of energy, we have change in kinetic energy plus change in potential energy should be 0. So minus half m v naught square, where this is the v naught we are talking about, plus potential energy at the point A, which is going to be alpha upon x, minus initial potential energy, which was alpha upon 1, should be equal to 0. So half mv naught square should be equal to alpha into 1 by x minus 1. Now let's substitute the values. So the mass was 5 kilograms and the initial speed we had given was 2. So this should be equal to 20 into 1 by x minus 1. So as you can see from this, we will get so this is the position where the particle stops. So the maximum displacement in the direction in which the particle was moving, maximum displacement before it stops, that will be equal to 1 minus of 2 by 3. This will be the maximum displacement before the particle momentarily stops. After that, again, of course, it starts moving along the positive x direction and it will make its way to infinity. So if we just want to find that initially we had projected it along the negative x axis with a velocity of 2 meters per second. So how far it goes before it stops and then turns back, then that value is the so-called maximum displacement we are finding over here. This one, as it turns out, will be 0.33 meters. So this is another example of the relationship between potential energy and internal conservative force and the type of problems you can do with it. Let's wind up with another example question. Suppose we have a force, a variable force in two-dimensional motion given by the relation okay, where x and y are coordinates in meters and the force is in newtons. So first of all, we have to show that the force is conservative. And secondly, if the potential energy at the origin is given to us as 20 joules, then find potential energy at a general point xy. So this is the question, just take a look at it. We'll discuss the solution. Okay, so let's understand this question. So first of all, we can see that if we want to calculate the work done by this force, in the two-dimensional plane, taking the displacement as a general two-dimensional vector and the force as the given value, this relation, okay, we can see that the work done by this force is going to be the dot product of these two, that is 2xy dx plus x square plus 2y dy, integrated from whatever initial to whatever final position. Okay. So we can see that if we were to define a third, let's say phi, such that partial derivative of phi with respect to x is 2xy and partial derivative of phi with respect to y is x square plus 2y. So this would tell us that phi is x square y plus some kind of function of y, and this would tell us that phi is equal to x square y plus y square plus some kind of function of x. So relating these two, we could see that we could just write phi as plus some constant, and where by default we can take the constant as 0. So we can do the substitution here. We can substitute phi as this new variable. So then using chain rule, we can see that t phi would be equal to this quantity. So hence so in general, the work done by this force would be defined by the relation x square y plus y square at the initial position, sorry, at the final position, minus x square y plus y square at the initial position. And we'd be able to see that this work done by F is path independent and equal to 0 in a round trip, which proves the point that the force is conservative. So this proves that the force is conservative. Now, once we have understood that the force is conservative, we can use the relationship of potential energy with work done. Delta U is negative of work done by this force. Okay. So potential energy at some general xy minus potential energy at the origin would be equal to negative of F dot ds from the origin to this particular point. So it would be negative of this integration that we had So as you can see, this would become minus of this relation from 0, 0 to x, y. And this quantity here would be the potential energy at the general position x, y minus the potential energy at 0, 0. Now this quantity was given to us as as 20 joules. And this we want to calculate. Okay. So now we have this expression. So the formula for potential energy as a function of the position becomes this. And this formula is such that it fits the given conditions. It fits the condition that potential energy at 0, 0 is 20 joules. Okay. And the force is x component is going to become 2xy. The force is y component. So the internal conservative force in turn fits the value that was given to us in the question. So that verifies that the solution we have got is the correct solution for the particular potential energy relation given or the particular potential energy derived. So with this, we conclude today's session, people. We have learned the important aspects of the relation between potential energy and internal conservative force. Next lecture, which will be our assessment lecture, we will look at some more applications of work energy theorem in particular, including the applications in vertical circular motion. So that's it for today, and wish you all the best.